Hello, hello. How you guys doing today? Happy Thursday. Hope you got your coffee. Actually, I am out of my... I got a little bit left. There we go. All right, we're going to be finishing up our Chapter 5, Array-Based Sequences today. Got more to talk about, some more terminology. And then we'll be able to try it ourselves in the lab. Hey, happy Thursday. Yeah, definitely. Let's see. Out of coffee at the moment. I've got... trying to be a little healthier here. It's not working quite so well yet, but that's okay. I've got these little cans of Perrier because I like bubbly things. It's very satisfying. And you can get these on Subscribe and Save on Amazon. I'm not an affiliate. I don't get money for you buying things on Amazon. But I just like when they deliver things to my door so I don't have to go out. All right. Oh yeah, here we go. Here we go. Our array-based sequences, we're going to finish up this week, Chapter 5. We'll have our lab on Monday, doing some array-based sequence stuff. Sadly, that one's not quite as interesting. I apologize. But we want to practice some of this array-based sequence code and try some of these things and see if we can make some of these things make sense. Do some timing exercises and stuff. So we'll see. We'll see how well it works. So we had talked about last week, no, not last week, on Tuesday, last Tuesday, excuse me, how the Python list itself, right, would auto-resize itself. So it's larger than it needs to be, and there's a good reason for that. We're going to take a look at that, excuse me, in just a second. Let's take a look at why that's a good idea. Remember we talked about performance in terms of time in relation to n. Right? The bigger n items I have, the more n items I have, the longer something takes. If it's linear, right, or if it's quadratic, or some sort of exponential, right, things get slower and slower and slower. So we're going to take a look at that. So that's oh yeah, it's loading up both projects again. I can't get rid of this project. Apparently, it just wants to stay open. Let's see what we get. Maybe. All right, there we go. Come on. Open project. Here we go, Chapter 5. In this window. That might do it. All right, awesome. So we were doing our random list, we were checking the size, and then we did this thing where we were looking for repeats. Let me zoom that in a little bit. All right, we said this one, for every n I have to check, has to check all the other n's. So performance here is n squared. It's the more n I have, the longer this thing takes. So these sort of measurements are important. So we measure, typically this is measuring the time. You can also measure things in space or like memory usage. Right? So in terms of memory usage, well, yeah, if I'm adding 1,000 things, I'm taking up 1,000, right? I still have that same 1,000. So the memory usage one isn't as important in this class as the time complexity. And complexity is our fancy term for, how is it? Is it linear? Is it exponential? And you can get better than linear, right? You can have a logarithmic growth where, it's the nice, it starts up and it starts tailing off. So it grows really, really, really slow logarithmically. Remember those curves from your math class? We can have things that are logarithmic, and we can have things that are constant, right? If it's no matter how many n items I have, if it just does one thing or two things or three things, that's called a constant time. So we're going to look at a couple of those operations here. So with the Python list, right, because it is oversized, and because we talked about when we create a list, or essentially it's an array in memory, we get a contiguous block. And we can put all of our references inside of that so we know where to go find things. We can get instant access to it. So the reason why we are oversizing, right, is if we imagine, let's draw this out here. If we have the list, right, and we add 1, 2, 3, 4 to it, and now we're out of room. When we need to resize, we actually make a new array in memory, and it's somewhere around twice the size. There's some good factor, I forget what it is. Twice the size is easy, and we have to copy all these things down. So if we have to copy n items, what's the speed, or what's that complexity in terms of n for this copy operation? What's linear in n? So we'd say it's n speed. Okay, for every n item, I have to make n copies. Or no, sorry, for n items, I have to make copies. So I'm going to make n copies for all my items. And then I've got room, and I can put a bunch more in here, right? So then I could do 5, 6, 7, 8, right? And then it might need to make another one. So make another copy. I got copy 8 things now, right? 3, sorry, I was saying 8, 4, 5, 6, 7, 8, and I've got room for a bunch more. Excuse me. So if we think about this with a little bit of math, and we're not going to do any super fancy math, but if we were to kind of graph this out and say how many operations does it take? So for n items here, this is our axis, right? This or our n items axis. So for 1 item, for 2 items, 3 items, 4 items, 5 items, 6, right? On and on and on and on and on, right? How many operations? Right, well, if my initial array starts with like 4, right, it's 1 operation. So this is like a constant operation here. As soon as I run out of space, though, it's going to take me n operations. So it'll take me 4, right? 2, 3, 4. 4 operations to do number 5. And then 6, 7, 8, right, are super fast. No big deal. And then the 9th one, when I have to do that again, this was going to go up to 9, or 9 operations, right? Because plus 1. Right, so I guess that would be 5, that would be 9. So that's to copy 8 things and put the 9th one in. Right, and then we can double. So then we have room for 16 more things, right? Or 8 more things after that, a bunch more. And then that one has a big spike. Right? If you zoom that out, right? As I shouldn't be drawing on top of it, but we can do a bunch more, and then it's another big spike. But each time, if I did this like actually nice on a piece of graph paper or something, right? The spike is just as long as the distance, right, between the next gap. So when my spike is 4, it's the same as the next 4 here. This spike here is the same as the next distance here. This spike here is the same as the next distance here, because we're doubling every time. So what happens is, remember, we have a couple ways of measuring. We have the best case performance, we have the worst case performance, and we have the average case performance. So the best case performance is it takes 1 operation. Just throws it in the next open spot on the list. Boom, it's open, we throw it in, we're done. Constant time operation. 1, 2, 3, whatever it happens to be, right? Not too big of a deal. Constant operations. No matter how many n I had in there, if I have an open spot, it fits right in. Done. The slow part, right, the worst case is if we're at one of those places where we're at capacity and we need to resize. So if we have to resize, it's going to take n operations. So if we're open, it takes 1. If we're full, it takes n. What is it on average? And this is why the doubling is actually important here. So if you imagine this picture, right, if you were to take these and actually lay them down, right, this direction, and lay this one down this direction, and lay this one down this direction, you have a line, right, that goes, it starts at 1, it goes up to 2, and it stays flat. Maybe there's a peak to 3 every so often. I think maybe that 1 extra operation will peak up to 3, right? And that's it. So if we lay them down, if we're averaging it out here, just you can kind of get the visual picture of that. If you just lay down all the peaks, they all fit into the gap because it's a doubling. So if I had 4, I'm going to double in size, so I have room for those 4 n operations to fit across the next 4 that go in with no extra work. So the average case, or the book will call it the amortized performance of this, is still constant. Still a constant. It's like 1 or 2 or something like that. And there's some funny rules. We're not really in math land here. So in terms of performance, when we talk about, so that you have, let's slide this up here. So when we talk about performance or complexity, right, you have constant, which it could be like 1, could be 2, could be 3, could be 100, could be whatever, right? But it's a fixed number per n, so it doesn't vary based on n. You could have log n, right? Remember your nice logarithmic curve, right? You could have linear in n, which is just a nice straight line. You could have exponential, which is, right, that's super high curve. And then you can even get, I think, what is it, factorial or something ridiculous, or n to the n or something stupid that's just like shoots way up. That's just terribly bad, right? N squared, n, I don't know. And it's something bad. It's no good. So most of the things we're going to be looking at will be constant, logarithmic, linear, or exponential. There's a couple that are bad, like that factorial, or I'm sorry, the Fibonacci example, right, is one of these, like n to the n or some n factorial is also really bad, right? Because like every new call spawned a bunch of other calls all the way down, which spawned a bunch of other calls all the way down, which spawned a bunch of other calls all the way down. I don't even know how to do the math for it. You can ask your linear algebra teacher, or no, the find a discrete math teacher. I'm sure she could show you the math for it. But does that make sense when we look at the complexity here? So we're saying constant, logarithmic, linear, and now the funny thing that happens, because this is not real math land, this is just theoretical here. We could say, hey, if our time, if we're doing like 7 operations for every n, and it's 7n, where did my 7 go? 7n, there it is. Right, so if I had 7n, we really just, we get rid of coefficients. We don't care about coefficients. So constant, because we don't care about coefficients, really just, it all goes down to 1, essentially. Right, like 100 log n still is logarithmic in n. We don't really care. Right? So you essentially just get rid of the coefficients. So we're only ever going to see 1 log n, linear in n, or some exponential. Right? We don't often use the coefficients. We just throw them away. Because, again, it's not all that important to the details. Okay? So then in terms of a Python list, right, how long do operations take? Right? We're going to look at our operations for our list here. Let's see, where is it? So a couple common operations. So you have an operation as like a table here, and then you have the time. So like to get the length is constant. They use this big O notation. I forget what the O is. They call it big O. I don't remember why. It's some Greek letter, I think. You'd say it's O of 1. To get data at an index is still O of 1. Right? Because it's a chunk of memory, contiguous memory, right, that starts somewhere x327 here, I just take the index and I multiply it by the size of a reference. And I can jump to the first item, I can jump to the second item, I can jump to the 100th item constantly. Constant time. It's just a quick mathematical operation, and I go read that memory location. So it's constant. If I want to count how many times a value shows up, well, that's add operations, right? Because I have to go look at all items in the list and see what happens. There's an index of a value. Now, this one gets a little bit silly. They use a term k, which is O of k plus 1. But essentially, k is just, wherever it happened to be. So if I found it first, it was the first thing. If I found it last, it was the last thing. If I didn't find it anywhere, it was n. So k is essentially n mostly. Doesn't have to be, because sometimes we're going to find it right in the list. Sometimes it'll be the first thing, sometimes it'll be in the first 10%, sometimes it'll be in the back half, wherever it happens to be. So it's slightly better than n, but essentially if an operation runs in k time, we say it's still linear in n. To check if a value is in, same thing, O k plus 1. Right, still k operations, right? Sure. Some other ones, if to compare one list to another. So list equals another list. Again, it's still this k operations thing, because we're going to take the first item of each, compare them, the second item of each, compare them, the third item of each, compare them, the fourth item of each, compare them, the fifth item of each, compare them. As soon as we find the one that doesn't match, we're done, not equal. But maybe we have to look at every single item of the list to see if we're equals. Right? To get a slice, right, to slice from, I don't know, what they say, J to K or something. It's a terrible slice. Right, is O of J minus K plus 1. So it's that chunk, right, because we're just reading that many locations. So that one's not linear. That one's based on how big a thing we're slicing. So that one, K is not always N, but like if you're slicing everything, it'll take everything. Okay, so it performs relatively well. You know, counting can be a little slow. Indexing in can be a little bit slow. We'll check some of those out. But essentially what we can do is we're going to try and build this ourselves. And this is sometimes interesting, sometimes it's really boring. So it just depends on how you feel about it. And we're mostly copying out of the book. I don't like the way the book does a lot of these because I find it confusing. Like some of his variable names are like A. That's just silly, right? So that's fine. So this is going to be our dynamic array. And I'm not going to use the C-types thing. There's this really cool thing in Python. You can use, it's called C-types to get, it's a particular type of data. So it's a little bit smaller array. You can do a real array with it. I'm just going to cheat because we're not going to use this anyway. And then it just makes everything simpler. And that's another reason I don't like the book. This is mostly sourced from the book. Okay? Trying to write our class for dynamic array. Right, it'll have an init. There we go. And right, what we're going to do is we're going to start empty. So self dot number of items is 0. Now again, I don't like he uses n. And then he puts a comment in to tell you what n means. That's stupid. If you have to put a comment in, use a better variable name, right? Self.capacity. Now this capacity is actually a little bit silly here. So we don't actually need this. So we're not going to use capacity because we're not using the C-type array. Right? We don't need to bother. We're going to have our actual number of items, and then we're going to have self.data is an array. Okay? Great. And then we actually probably want to have a couple spaces in here. Yeah, that's fine. We can just do it like that. Okay? So then we're going to add our own length definition. And we're going to return self.number of items. Remember, we're going to track internally how many items we have for our length. And then we're going to have a get item. So get item is the special operator to use those square braces to say at index of. And I'm going to use index because I think K is dumb as well. So give me an item. So we're going to check first. So we're going to say if the 0 is less than or equal to index is less than or equal to self.number of items, or less than self.number of items, right? Because we don't have an index there. So if it's there, great, we're going to return self.data at the index. Otherwise, we're going to raise an index error. Okay? So again, he does it the opposite way. That's fine. I don't really care. One way or the other is fine. He had a not in here and you raised the error. Maybe that's better. Sure. Why not? If not. Okay. We'll follow the book's example. Okay, so if it's not in range, we raise an index error. We don't have that index. We're going to add our own append method. Self in the item. If you want to add the item, great, we're good to go. So first we need to make sure that we have room. Right? The reason we're doing our own data storage, making this thing bigger than it needs to be, instead of using C-types, we're just going to do it ourselves, which is okay. So we need to make sure we have room. So we should start this off at 1 here, right? So I'm going to put none in here. That's just a special placeholder. There's nothing here. It's a none item, just so I have 1. Okay, so we're going to say if my self.number of items is equal to the length of self.data, then I'm out of space. I need to resize. I need to make myself bigger. Right? I'm gonna get bigger. So we're gonna take self dot. Let's make a new array here. So we'll say we've got a new list. So new data is a list. I think it's none. If we say times length of self.data, self-data times 2. Right, I think we can do that. So this should give me the list of the right size. We'll check it out, see if that works for us. I think that'll do what we need. So if we're not big enough, we need to make a bigger list. Then we need to go through and copy. Right? So then for item in self.data, right, we need to go move it in. Well, actually, let's go by index here, right? So we'll go by, for index in range, the length of self-data. Let's take new data at index is equal to self.data at index. Let's just copy it over. Right, this is doing that copy step that we did, right, where we have to go and say, where to go in here? Here, I need more space, so let's copy 1 down, let's copy 2 down, let's copy 3 down, let's copy 4 down. And then we got extra room here. We're just copying things over. Then we say self.data equals the new data. And we replace ourselves. So if we need more space, make more space. Then we're going to go add in the item. So now we don't want to use the append method, right? Because we have a bunch of these nuns in here. We want to set self.data at the self.number of items equals the item, right? Because this number of items is the next available index. If I have 0 items, it goes in slot 0. If I have 10 items, it goes at index 10, which is the 11th thing. So we just put it in there. Then what we need to do is make sure we take self.number of items and we add 1. Right? We're making ourselves bigger. Okay? Does that make sense? So we can try it. So we're just making our own dynamic array. Essentially, we could do this if we didn't have the Python list. I know we do it with a Python list, but it should be fine. So let's try it and see. Let's see. We have a main over here. That's fine. We'll just do it in this one. Let's create a new dynamic array. Dynamic array. Test array. Sorry. Test array equals a dynamic array. And test array dot append. Let's add some values. So let's say for number in range 10, let's try and add 10 items. Oops. So we'll append the number. Right, and then for index in range, the length of test array. Print test array at index. Okay, that'll call this get item function here. That's the indexer. The get item is this at index of. So let's see if it works. I'm going to put it in debug mode and let's watch it. And just put the breakpoint in and run with debug. Okay. So we're about to make the array. Let's step into our code. Let's see the constructor. We're going to set number of items. We're going to have a new array, right? It has data with a none in its 0th thing, because we want to have at least one thing to start. Right, and then we're going to we're about to append, so let's step into the append method. We're going to check, is my number of items 0 equal to the length of self-data? Remember, the length of self-data should be 1. So that shouldn't be true. So step. Okay, great. So now we're going to set self-data at my number of items equal to the item given. Then we're going to increase our number of items. Okay, good so far. Now we're going to add the number 1. Let's step in. Now we have 1 item, and the length of self-data should be 1, so we need to resize. So we're going to make a new data array. Let's see if that one works. So new data, yes, is a list of none, none, double-sized. So it's 2 nones. So this is actually bad, but we're not caring about performance. We're not actually trying to do anything that's very performant, because we're skipping the whole C-type thing. Okay? So we have a new one. Now we're going to copy the items out. All right, we copied out the 0. That was it. Now we're going to change data to be the new data. So my old self data is going to go away. Right, that list will get garbage collected. We set the next value. Right. We increase our number of items, and we're done. Now let's step in. So now we're going to add the number 2. Our length here of self data is currently 2. We have 2 items. Uh-oh, we're going to have to increase our size. Right, so let's double. So now new data is size 4, 4 nones. So we should have some more room. So now let's copy out the 0. Let's copy out the 1. We're done ranging through the old one. And now old data becomes new data. Then we can add data, the next thing, there, and increase our number of items. So now we have 0, 1, and 2. Same thing with 3. Let's step in. So now we're going to do 3. We have 3 items, but the length of our data is 4. Right? So we don't need to increase our size yet. So we should just be able to assign it. We're good to go. Now we're going to add the number 4. Oh, we're going to have to resize again. So with the resizing, as long as we're doubling, like we're doing that geometric growth here, we're going to be okay. So it's going to resize. We'll copy the values out, right, into new data. Now it's a size 8. So we copy the first 4 out. 0, 1, 2, 3. Swap data for new data. Add the next item. And we're good to go. Okay, so that seems to be working okay. Let's come back to here. I'm going to move the breakpoint to there. I'm going to hit continue. Okay, so now let's see if we can get our values out. So let's check. So our test array has data. It's got 0 through 9. Sorry, it's a little bit small. I can't zoom that one in for you. But then it's got some additional room, right? Because we're size 16. Because we're doubling. That's right, we have some additional room. It's okay, not a big deal. So now let's see if we can get a value out. Let's step into our code. And we're going to check index. 0, greater than or equal to 0, less than my number of items. Number of items is 10. I should have a 0. So I'm going to return whatever's at index 0. And we just on and on and on. We'll just we'll take that breakpoint out and continue it. We see our output, 0 through 9. That one I can zoom. We built our own list, sort of. I mean, we're still using the Python list, but we're doing it ourselves now. So and really, like this could be sometimes we'll put this in a helper method to call resize, which is nice. So let's do that. Let's use the tool. So I'm going to right click. I'm going to say refactor. I want to extract method. I'm going to call it resize. And notice I use the underscore to mark it. Hey, you shouldn't call this one publicly. This should not be a public method. This is just a private helper method in my class. So if I need to resize yourself. And then I can assign the data, right? So it does all that same stuff here. You okay with that so far? And we're just doing the same thing the Python list already does. We saw, based on its size, that it resizes itself every so often. I forget what the actual factor is. It's something. And I'm sure it's good because smart people looked at it. People way smarter than me. Right? Python's been looked at by lots of people. So it should be in good shape. Right? Just pausing for questions here. Yeah, well, so if we understand what it's doing, we sort of understand the performance of this. Yeah, the inner workings and then how it performs. So like to get an item by index, sure. Now, what if we wanted to get something by value? Right? With our Python list, there's I forget what the thing is, self.data. index of a value, right? We get the index of an item. We could add our own index method. Kind of silly, but that's okay. We can do that. So define index of an item. We're going to say for index in range. I guess we can just do for item, right? For item. I can't call it item. That's right. So we'll just do index. Index in range, the length of. Now we don't want to range all of self data because I only need to range number of items. So I don't need the length. I can just do number of items. And I can say if self.data at the index is equal to the item, return index. You found it. If we didn't find it, what do we do? Does that throw? I'm trying to remember now. Self.data index. Huh. How do we get back if it doesn't exist? How don't I remember that? That's right. So some list is a list, index equals some list, index of 10. I don't know. Let's see what we get. Oh yeah, yep. A value error. There we go. So if we didn't return, right, on our index of, we're going to raise a value error with item not in list. I don't know. Formatted quote, sure. In dynamic array. Sure. And just give it some message. But we can see here, so the performance of this is either going to be K because we found it, or N, we had to look at all the things, and then we throw an error anyway. Right, so we can write all those same methods here. We could write a count, right, if we wanted to. Find count of self and an item. So now we don't have to use the, I guess we might as well, because we've got it here already. So we're going to have a occurrences 0, and then we're going to loop occurrences. Did I spell it wrong? Oh, it's never used. So if we found it, we'll take occurrences plus equals 1. When we're done, we'll return occurrences. Right, we can count how many times this item shows up. If it matches, sure, it showed up. We found it. Now did I spell it wrong? Yeah, typo. Rename. Occurrences. Look at that, it even renamed all for me. That's so helpful. Thank you, PyCharm. So we can do the same sort of things. We can write our own methods for them if we want. And he goes through all the fancy math, which is really cool. There is a downside to this. So remember we talked about performance in terms of time and performance in terms of memory, or complexity in terms of time and memory. If we start removing items and we're still really big, well, we're still taking up tons of extra space, which is a little bit unfortunate. But that's okay. It's not the worst thing in the world. Oh, excuse me. I wonder how Control F works in a browser. I'm sorry, I missed that comment, Eric. Is that how Control F works in a browser? Like trying to find something? Yeah, I mean it has to go through every word in the source and find it. Yeah, it probably doesn't keep it in a list though. It's got like the HTML document. I don't know how it searches that sort of thing. Okay, so now let's look at a couple other operations. Right, we looked at some complexities. of some of these items here. We said, okay, these were all O of n or k, right? So other things we could do with the list, right? So we said, hey, appending is essentially O of 1 on average. Right? That's really the average time, running time here. We know worst case is n, but on average it's still constant. So I know it's not 1, it's probably like 2, 2.5, 3 or something, but again, we throw away coefficients, we don't care. Okay? Sorry, don't need to zoom that too far. Okay? Other things you can do, you can insert at an index. So to insert something at an index, right, if I have my list over here, and I've got 1, 2, 3, 4, 5, right, that's indexes 0, 1, 2, 3, and 4. If I wanted to insert something, say at index 2, say let's put another 2 in here. Assume there's room over here too. But what has to happen is I need to go move everything down the line. So 5 has to move in here, 4 has to move in here, 3 has to move in here, and then I can put the 2 in. So the performance is your index, or so it's n minus the index here. So if you insert near the end, it's pretty quick. You only had to move a couple things. If you insert at the beginning, you had to move n things. So this one could be really slow, right? To remove a value, right? Remove a value, it has to go look at essentially n things. Really, I mean, sure, it's k, it's the first time we find it. That's fine, but, you know, we have to go find it. Oh, I'm sorry, no, it's not even k. That's right, because when we do remove it, right, so say we found a 2 here, and we're going to remove it. We did it within 2 operations, but then everything has to slide back into place to backfill, because we can't have open spots in our list. So it took up to k, and then it took the rest of k to n to backfill. So it does take all of n to remove something, because it has to fill the gap there. Okay, a reverse is O of n, takes n items to reverse. We have to do the swaps. You can do it with n over 2, but again, we throw away coefficients. Really, that's like 0.5 n, right? And we say, oh, we don't care about coefficients. Throw them away. So it's still n for a reverse. Then there's a sort. Now, sort is really cool, and really smart people have worked on these kind of things before. So you can sort in n log n. You can make your sorting time be n times logarithmic of n, which is still better than n, which is way better than n squared. Right? And when we get to sorting later, we'll look at different approaches to sorting. The naive approach is take an item and see where it goes in the list. Put it in the list. Take the next item, see where it goes in the list. Put it there. And it's really slow. Right? So there's better ways to sort, and we'll look at some of those better ways later. So we care about performance time because the different data structures we're going to look at perform differently for different operations. So if my operations are heavy on inserts and removes, a list is actually a really bad data structure for it, because all of the operations are going to be n times. So we can find better data structures that perform better for inserts and removes if that's what we're going to be doing with our application. And we'll look at some really cool data structures, and then some of the memory stuff will matter a little bit more when we get there. But for the first couple, it doesn't. Okay, so let's say we wanted to do our own insert. Why not? Let's insert. Define insert at index the value. Okay. First, we need to see if we need to resize. Right? Because when we're adding something, we might be at capacity. And now I'm feeling bad that I have the same check in here twice. Right? So I'm actually going to take this one here, and I'm going to cut that out, and I'm going to rename resize. I'm going to throw this in resize here. And let's refactor, rename this. So we'll say check and resize. Yes, do the refactor. Okay, so the first thing we can do is self-check and resize if we need to. Okay, so we check and resize if we have to. If we're at capacity, it resizes. If not, we don't. Right? This way I don't have the same code in here twice. I'm not going to feel bad about myself. Okay, then I can go start moving things. Right, so I'm going to have for index in range, and I'm going to start here at self.number of items. I'm going to go down to the index, and I want to step by -1 because I want to go backwards. So I want to start at the end. If I had 10 items, I want to start at 10 and go back and back and back and back till I find the index I need to put it in. Okay? So I'm going to start moving items. So I'm going to say my self.data at the index is equal to self.data at index -1. Because remember, the number of items that I have is one index greater than my total number of items. Or the index of the last item, right? So the number of items, if I have 10 items in a list, I have indexes 0 through 9. So I'm going to take, here, let's look at an insert. So if I have, say, I don't know, we'll just do what the indexes do. 1, 2, 3, can't, 1, 2, 3, 4, right? If those are my indexes here, but I have room additionally out through 8. I have 5, 6, 7, 8, whatever. So if I have items here, if I have a 1, a 2, a 3, and a 4 here, and I want to insert at index 1, I want to put another 1 in. So it's going to say, okay, give me, I have 4 items, get started at index 4, put the thing at 4 minus 1. It puts the 4 in here. Then it says put the thing in here, 3 minus 1. Right, put the thing in here, 2 minus 1. Once I get down to the index, I want to stop. Right, because it's not, ranges are not inclusive, so I'm not going to actually do index. So I've moved all the data, then I can say self.data at index is equal to the item, or the value. Should we call it item? I think we were using item before, right? Call it the item. Might as well be consistent. Right? Then, don't forget, right? Because this, I forget this all the time, we added an item. Self.number of items plus equals 1. I forget that all the time, and it screws everything up. Okay? And we could check, right? We might want to make sure that index is valid. Right? So let's do that. Let's do this. We already did it once here, so let's do it again. So let's refactor. Let's extract method is valid index. Okay, and we can just do that again. Why not? So make sure it's a valid index, then check and resize, then go for it. That makes sense for an insert at a given location? And how about a remove? So define remove item. Right, so to remove an item, right, we need to go find it first, and then once we take an item out, we need to backfill it, put everything back after it. Okay, so we're going to say for index in range self.number of items. Right, we need to go find it, see if we can find the value. Right, we're going to say if self.data at index is equal to the item, we're going to remove it and start backfilling. Okay, so if we found it, start replacing all the things. So now we're going to do another loop. We're going to say for index to, I don't know, replace in range. Now we're going to start at index, and we're going to go up to self.number of items. We're going to take self.data at the index to replace is equal to self.data at the index to replace plus 1. And this one actually we want to stop one short. No, that'll work. That'll stop us one short. We're good there. right? So we're going to loop. If we find it, start the next loop to start replacing things. So starting that index, start dropping things back on top of it. Drop the next thing back, drop the next thing back, drop the next thing back. Okay? Then when that loop is done, we want to set my self.data at self.number of items. Actually, let's do this. Let's do that. It's like self.number of items minus equals 1. Right? We have one less item now. Right? Then that one gets set to none. Because we had a duplicate here, right? We copied the last one out, and it's in the last index plus where we thought it was before index. So we're going to put none back on top of it to empty it out. And then we return. We're done. Bail out, right? If we went through all of our items, we didn't find it, we raise a value error. Error. Value not found or something. Right? So try and find it. As soon as we do find it, loop through and backfill. Right? Start replacing, and then back out the item. We have one less item now, and put a none in there. And this leaves room for the next thing to go. And we have to free it up. We put the none in there to make sure it cleans up after itself. Because if it was a reference to something, Python would hold on to it because it's still in our list. So we put a none in there to make sure it can get garbage collected. Right? How you feeling so far? Okay, cool. All right, so it does talk a little bit about the insertion sort. Don't worry too much about that. We'll get back to that when we get to sorting and sequences later on in the book. But if you want to take a peek at it, it's cool to look at. No, it just inserts and removes are slow in lists. That's just what it is. So there's other data structures that are faster. So you'd use a different data structure, really. But like if you have to have a list, it's just going to be slow. Yeah, I think the rest of that's pretty good. Cool. That's got most of it. He goes into a couple other examples there in the textbook. They're interesting and all. I wouldn't worry too much about them, but like read through them, find them interesting. But if it's a little fuzzy, that's okay. If it makes no sense, let me know. We can talk about them for sure. But if it's like you can mostly follow along, then you're in pretty good shape. He just has lots of examples for these list type things, and I don't know, I think that's a little silly. Yeah, multi-dimensional lists, we have that. We have that. Sure. Tic-tac-toe, okay. Yeah, it's fine. Awesome. Yeah, I think that's all we got then. We can end just a little bit early. Don't forget, coming up, what do we have coming up here? Project 1, the backtracking recursion. Yeah, let's do the rubric right now. Sorry, thank you for that. Edit. More options. Let me put that in, sorry. Come on. Load for me, friend. So this one is coming up due next week, 3:30. I'll be going over the solution. So hopefully you guys have started on it already. Okay. Where's my rubric button? Am I going crazy? What did I do wrong? Where's my rubric button? Points? Points? There's search? That's not it. Find rubric. What? Alright guys, I'm going crazy. I'm sorry. That's... Okay, sure. Go to rubrics. Add a rubric. Project 1. Shoot, let's go back to the assignment. I'll be able to see the definition here. Wait, I don't... Usually there's like a button to assign, and I'm really confused now. Maybe because someone already submitted? No, now I have a button. I was in edit mode. Yeah, outside of edit mode, you can add a rubric. Of course, Eric is just dumb today. Let's close that one then. Not in edit mode. Let's add a rubric. There we go. Project 1. I felt like I was going crazy for lots of reasons. Okay. So maze solver class. Maze solver constructor. Or init, right? Init. It accepts a 2D list for the maze. 2 points. Maze solver solve method uses backtracking recursion. Solve the maze. There's other ways to solve mazes. I'm well aware of that. I know they're out on Google. I'm not dumb, despite how I look. Okay? Don't copy one you found online. If it looks funny, I'm going to ask you to tell me how it works. Not to be disrespectful or anything, but the odds of you explaining some of these advanced maze solving algorithms to me is low. Is that fair to say? Right? And if you can explain it, great. And if you can explain the A-star pathfinding stuff to me, I'll be blown away. You can have the points. Okay? But if you can't, no good. So just do your own backtracking solution. Okay? So backtracking recursion. Do 4 points for that one. And then maze solver solve method. I might not even have to return. It calculates the shortest possible path. And let's do 2 points for that one. And maze solver unit tests. Give it some test mazes and ensure it works. 2 points for that one. So not as heavy on the unit testing points this time, but 2 points for your constructor. Your init method takes any maze to-do list. Right? It will backtracking recursion to solve the maze, 4 points. Calculates the shortest possible path, 2 points, and then unit tests your maze, make sure it works for 2 points. So if you can't get the shortest possible path thing done, but you can solve it once, and you unit test it, you can get 8 out of 10. Okay? Does that sound fair? All right. Is that agreeable? One person already submitted, so if you don't like the rubric and you feel like I misled you, please let me know beforehand, or you're welcome to also change it, but I'd be happy to talk with you first. Right? Don't do a bunch of extra work. But I think I pulled it all right from the description here. Does that sound good? Yeah, it's no problem. Yeah, we've got another week to get it in, so go for it if you got to resubmit. Then we can chat after. I've got office hours after class today, after class Tuesday. and then it's due Thursday, and I'll go over my solution in class on Thursday. All right, awesome. If you guys don't have anything else, I'll be hanging out on Discord to answer questions. We can fire up some screen shares, or I can do Zoom, whatever you guys need. We can chat. If not, I'll see you in lab on Monday, or I'll post the lab assignment Monday, and I'll hang out again in Discord. Let me know if that works. I'm open to changing formats if you guys think something would be better. I think it's worked out relatively well so far. People can just ask questions in like the general class chat room, and then if I have to hop on screen shares, I can hop on screen shares with people. And I think that works out decently. Again, the goal of labs is that you get them done, right? I'm going to go over solutions to labs because I want to make sure you guys get them done and you understand them. But if you wait to do it until I've already shown you how to do it, and then you just copy paste my stuff and don't understand it, it's going to go poorly for these projects. Okay? All right, folks, you take care. I'll see you around.